So to start with, what is robot co-design? So robot co-design is actually a joint process first of all, optimizing the control, or you can say the behavior, or even the brain of the robot, and simultaneously optimize the design or the morphology, or you can say the body of the robot. So control normally refers to something that can be adaptively changed in response to different environmental conditions. And design, or like bodies of the robot, normally remains fixed throughout the entire execution. So to give you a more concrete examples of what like soft robot design can be, is first of all, it consists of the shape or like the geometry of the robots. And second, like how you place your actuators, what the mechanism to generate force from your actuators. And finally, different type of material properties, including like body stiffness. And why this is an interesting like research topic is because intelligence can exist not only in the brain, but also in the body. So in the nature, there are a lot of very cool and amazing natural creatures that exhibit some kind of morphological like intelligence that allow them to like traverse through different terrains or do a lot of amazing stuff. And taking inspiration from the nature, there are also like a lot of roboticists and researchers that try to mimic like natural creatures and try to like copy this kind of morphological intelligence and then allows the robots to have better capability of doing various tasks. And on the other hand, our research also showed that not only in the nature, but when we put it into the computer or in silico, using computational methods, we can actually like simulate different type of natural creatures and then put them into a lot of different terrains and see how they behave. And the interesting stuff is there are actually a very interesting intertwined relationship between environment, morphology, and also their motions. So for example, among all the like different kind of animals, like caterpillars kind of excel in this kind of muddy environment by left and right undulating their body to disperse the mud to move forward. And another example can be in this very low friction icy land, like it's hard to actually propel yourself using friction. So basically how you can, like, let's say, for example, rotating yourself is flapping your tail to create a more like a normal force. And one of my favorite examples is this, like among all the animals we tested, like fish somehow like move very well in desert. And it's like result from computational methods, but also it makes a lot of sense because there are a lot of friction in sand. So it needs to like sort of lift its torso to reduce the friction to move forward. And also we tested like using computational methods to design a swimmer. And this is what we get, something like a fish-like creatures, and it's streamlined, and it can move very fast in the water. And okay, so I talked about one part of my talk about robot design. So let's switch gear a little bit to go from the physical robot world back to the digital virtual world, where there are tons of excitement that happens recently. So I believe all of you guys have already used this kind of cool generative AI technology in your day-to-day jobs, or even like already have it well integrated into your workflow, including like this can help you write your email. It can help you like create graphics or edit images, or sometimes for me, help me write my papers. And there are also research show that like this kind of technology can actually like improve a lot on the productivity of like people. And specifically, they increase the performance, like they reduce the time of working on stuff. In general, it's basically an amazing tool that can assist humans on their jobs. So up to this point of the talk, I wish I kind of trigger you guys to start to think about, what if we can use generative AI for robot design? And spoiler alert, the answer also, like echoing the previous talk, yes, we can. And there are several good reasons, like we figured that can use generative AI for robot design. So first of all, a lot of generative models, it's learned from large-scale 3D data set, so they've got very good generative priors. That it gives you sensible, well-structured 3D shape for you to start with for the design process. As second, there's like inherent connections to language. So this allows a natural interface for human to interact with your generative power robot design pipeline. And finally, a lot of these generative models actually operate in the lower dimensional latent space. So this is very good for optimization. Okay, so generative AI for robot design sounds like a really cool and brilliant idea. That's quickly tested. So now here I'm showing is we ask ChatGPT to design a robot. So basically we ask, please help me draw a new research robot concept. Draw me a schematic for a soft robot that can pick delicate fruits off of trees. And after a few seconds, this is what we get. Okay, first, at the first glance, I got to admit that like these are very, very cool graphics. And also, there are some kind of wild and crazy ideas on how ChatGPT thinks what we can do in the design. And specifically, I like this kind of robot. I like this strawberry robot a lot because it got some kind of mechanical structure in it. And also, like the strawberry torso in it kind of like implies that this is powered by some kind of very fancy nuclear source or something like that. So let's look closer on this one specifically. So this is cool, but is it actually useful for robot design? So first, we notice on the top of the robot, basically, it sort of defies the physics. Because if you look at the stem over there, the thin and brittle structures, it for sure cannot hold the mechanical structure of the robot arms. And second, if we look at the arm specifically, there's no functionalities because there are two ends that basically connect to the stem and also the strawberry torso. And finally, how do we even, although this is very cool, very vibrant colors, but how do we even fabricate this strawberry stuff? So what we are doing is try to basically integrate physics into generative AI. So let's start with generative AI models. And then throughout physics-based simulations, we can try to augment whatever that's required for robot design into the generative process. And then finally, we can actually fabricate the physical robot and show it in the physical world. And I want to quickly, just very briefly introduce this diffusion-based generative modeling. This is the most dominant generative model so far in the generative AI space. I won't talk to the detail, but I would like you guys to imagine the animations of a scattered cavity, like a random noise. It can magically, throughout the diffusion process, kind of converge and start to construct some kind of well structures data, like a cat image over here. And now think of this process as like a 3D process. We basically view this kind of process as like a growing of a robot. So that cavity is something like an embryo of a robot that contains all kind of chaotic components, but at the same time, the unlimited potential of what robot can be. And then throughout the process, you'll converge to some shape. And what we did is basically try to integrate physics into this growing process. And another thing is, you can notice that at the top of the diffusion process, there's a thing called embeddings. So this is something that can control your generative diffusion process. And how I like to look at it is basically, this is something like a gene of a robot. So we can not only use physics to modify the growing process of a robot, but also sort of hack into how the gene can be constructed into the robot. And this will give us generations that are not only capable of doing stuff in the digital world, but also doing something that can exist in the physical world. So now, having this pipeline, we can basically ask, please design a robot that can walk forward. So with the growing or the diffusion process, we can basically from something like a random noise, and then it will converge to this kind of like a quadruped robots. And then I want to emphasize again that throughout the growing process and also the generative process, we run physics-based simulation to actually provide the guidance of the generations. And finally, we can fabricate it in the physical world. And then Another thing I want to highlight here is basically this costs, the entire process actually costs like 6 to 7 hours of computer time, and then roughly like 30 minutes to 1 hour for human to actually put it into the design software, and then use 3D printer to print it, and then another like 12 hours for the printing time. So basically there are tons of like machine time, but for human actually spending effort on it, it's only like less than 1 hour. There are other examples, like for example, this is designing a robot that can pick things up. And we also showed that it can work in physics simulation and also the physical world. And this is another example that we can design a robot to move an object. So it basically know how to generate a robot that can sort of curl and drag the object. Okay, so far it's cool, but how far is it still from the human design? So this is Byung-Chul, like our beloved postdoc in our lab that works with me a lot on the hardware side. And this whale robot is what he designed. So look at the complexity and how large this system can be. So it seems like we are still very far, but in what aspect we can improve? So the thing that we are still working on, and also like we identified that there are several aspects that we think is super important for Gen AI powered robot design pipeline, is first of all, editability and controllability. And recall that I mentioned there are a connection to natural language. So there are several ways that we can do it. For example, like when we do like text to 3D, we have some success on, for example, this is a hurdling robot, and then we ask it to not only generate a hurdling robot, but also grow a pair of wings. And then it's sort of gives you a wing at the back of the robot. And another potential and promising direction can be doing like text to 2D and then to 3D. And the reasoning here is because there are much, much more data in the 2D space comparing to the 3D space. So your generative models performs much better in the 2D space. And then our job is try to like project that signal to the 3D space. So for example, this is like an example of a broom with 2 human arms attached on a stick. And then we can actually have a 3D shape of that. And then we can integrate that into a robot design. And finally, so think about the large like whale system I showed you on the previous slide. When people, like human experts are making their robots, they don't actually just think only globally. They also think locally. So what we are exploring is basically try to do some kind of local edits. Another aspect that we can improve the pipeline is basically integrate like human design components into the generation process. So basically, if we have like a input of, oh, please give me a walking robot, we basically have a human design toolbox that design that's collected from tons of like very good roboticists. And then we basically can use like language model to do like sort of common sense or knowledge-based reasoning to see, oh, which components can be suitable for this walking task. And then we can retrieve or select one of the components that can be relevant. And then we can integrate it into our design. And for example, this one is the walking teapot. So it will sort of grow a leg in the below of the teapot. So combining this all together, this gives us a very cute little walking teapot. And then this is from a Gen AI powered robot design pipeline. And so hopefully we'll use this technology to generate much, much more robots and do more customization and do some crazy design on the robots. So finally, I would like to conclude with my vision on this kind of technology. So basically, Gen AI powers robot code design pipeline allows a more efficient way and to design robot. And also because it's more efficient, so you can do more customization. And even more, what I'm mostly excited about is the democratization of this technology. So I hope to, like, some years afterward, like, we can enter a world where, like, even 10 years old child can just use their computer and then design, with the assistance of generative AI, their own favorite robots. Thank you.